Hi everybody, pleasure to meet you all and thanks for coming out, great turnout. My name is Eoin Wickens. I'm a researcher here, and this is Marta Janus. We're both researchers in Hidden Layers, basically ML research team. So we look at ways of securing artificial intelligence systems, but part of that is also looking at how AI systems can be attacked. So we're going to talk about the risks that AI systems face, how these systems can be attacked, and for what purpose. So after a brief introduction to why AI is so important and how ubiquitous it's become, we'll look at the who, the why, the how, and then explain the classes of attack, focusing on some real-world applications, examples, and mitigation strategies. So the last few months have been, nothing short of revolutionary. I mean, everybody's heard of ChatGPT now. My grandparents are asking me about ChatGPT, and when that starts happening, when they know what you're looking at work, that's kind of a big deal. So, ChatGPT has really taken the world by storm in a lot of ways, but we're not really going to talk about that today. But, it's just important to kind of highlight how AI is becoming so present and prevalent within our lives. Microsoft has Bing, Google has Bard, albeit to varying levels of success. But, I think it's taken us all by surprise at how quickly this has become part of the mainstream. But it's not just LLMs, it's not just ChatGPT and the likes. It's also, specialized image generation models, such as DALL-E, Stable Diffusion, Midjourney, which have been redefining the creative sphere and, allowing people with sentences to create incredible scenes and so on. And, getting into some hot water with, legal copyright issues at the same time. But, it's easy to see that it's becoming the zeitgeist of the decade. So, it can also be immensely helpful in both science and medical applications, such as drug discovery, mathematics, astronomy, medical imaging, and like pretty much anything that you can think of. And hopefully it'll lead us to many more discoveries and breakthroughs. So these here are just some basically recent headlines that we found. But in fact, AI has actually become part of our lives much before that as well. It's been used in more kind of evident applications such as self-driving cars, obviously, and, cybersecurity for things like spam, malware, intrusion detection. Also in applications like biometric authentication, your phone, Face ID, e-commerce, financial forecasting. Even when you apply for a loan, it's all the documents you send in are being approved by a machine. And it's quite interesting and amazing, to be honest, that, ML has so much power in our lives that it influences nearly, I'd say, a lot of the decisions that are made about us and for us during the course of our day. But with great power comes great responsibility, and we'll dive into that later. So first, we're going to take a brief look at how AI works under the hood, and for that, I'll pass you to Marta.
Thank you. All right. Let's start with just some basic terminology that we will use throughout this presentation just to make sure that everybody's on the same page. So sometimes there is a bit of confusion between artificial intelligence and machine learning. Some people use those terms interchangeably. There is a slight difference though. Artificial intelligence is a more generic term that describes any system that has the capacity of performing some actions that human perform, or in other words, it mimics human intelligence or human behavior. Now, machine learning is the technique that modern artificial intelligence uses to learn from the data and to improve itself. At the core of each machine learning solution lies something that we call machine learning model, which is basically a decision-making system that is responsible for reading the input and producing an output, so a prediction or whatever this machine learning model is providing. Where am I jumping? It's a very second slide. Sorry for that.
I think you're hitting space, so just hit this one.
All right, thank you. Machine learning model is produced in the process called training. So before it can be used, it has to be trained. It's basically a result of running a large amount of training data through some complex mathematical algorithms. After the training, which sometimes takes more than one attempt, so the model has to be retrained with different parameters in order to actually be more accurate. After that process, we have something that we call the train model, which can be then put into production. In other words, it can be made available to the end user. That is made through an UI or an API or any kind of access that lets the user query the model and receive the predictions. The input that the model takes can be anything really. Can be an image, can be a video, can be a binary data, or more recently a prompt, a text prompt, like for ChatGPT, for example. And then this data is processed by the machine learning model in order to produce an output, which can be a classification, a prediction, a real value number, or a text or an image. Like in case of large language models, it's gonna be a text. In case of image generation model, it's gonna be an image. So that's basically how it works. It's a little bit like a human brain. And most of common complex machine learning solutions use a technique called deep learning. There are other types of models as well, but we're not going to delve into it. We just want to mention something that we will be mentioning later on. Deep learning models are basically made of layers of neurons, another reference to human brain. And each model contains an input layer which receives the input from the user. It's not the exact input that the user provides, it's a vectorized input. So it's basically an image translated into some floating point values, or a text, but it's not a text, it's text translated to those floating point values that are understandable to our model. That's the input layer. Each a neural network model also contains an output layer, which produces the actual prediction or the output. And in between, there is a various number of so-called hidden layers, which are responsible for the processing of the information. So all the magic takes place there. This technology is really powerful. It's very impactful and it's very useful, but also it can be used against us. It can be exploited, it can be misused, or it can be used for malicious purposes. So why people would like to abuse this technology, and how? The answer to the question who could abuse it is simple. We have our usual suspects here. First of all, cyber criminals who are actually attacking machine learning models, not since today. It's been a good couple of years, a good few years since first machine learning solutions appeared on the market, where cyber criminals were already actively trying to mainly evade them. So like, for example, spam detection models were one of the first to use machine learning in the space of security, and the cyber criminals circumvented them pretty quickly. That's actually an attack against a machine learning model. So trying to evade it, like evade detection of spam or malware, that's an attack. And we have it going on for many years already. Other people who might want to exploit it are competitors. So some people who don't want to spend time or money on training their own models, they can actually try to steal the model from their competitors in order to get a cheap advantage. And on top of that, we have also sophisticated actors, for example, nation states that might use machine learning models for their nefarious purposes, like misinformation, like manipulation of the public opinion, and so on. The attackers can have various access to the model itself. So in case where the attackers have full access to the model that they attack, including the training data and the parameters the model was trained with, we are talking about white box attack. Now, this doesn't really happen often in the wild. It's something that belongs to the sphere of academic research, mainly. And yes, it's difficult to imagine attackers having this kind of information that is really sensitive and presumably really well protected. But it can happen in case, for example, of insider threat or third-party contractor who was tasked with training the model. This third-party contractor can be actually malicious and gain access to this information. The attackers can also gain access to some of the information doing open source research or by doing a traditional security breach. There is some tooling that the attackers can use. Owen?
Yeah, cheers. So adversarial ML has largely been within the realm of academia for some time now. I think papers started first coming on the scene back in the early 2010s. I think the preprint store, or not store, but the preprint repository archive has, or arxiv if you pronounce it, is I think up to about 4,000 adversarial ML papers now. So it's expanded, but while it might seem that attacking ML models requires a PhD in data science or advanced statistics or something of the case, it's largely not the case anymore. And this is largely thanks to the many free available attack frameworks, which can be used as pen testing and evaluation tools also, primarily, that have been released over the past couple of years. So some of the tools that we show here implement these research level attacks, like IBM's Adversarial Robustness Toolbox. Others then act as abstraction layers upon things like art, which allow kind of like an ease of use. So you can make it a bit more metasploity, if you will. Others then, augment image generation or text generation. So Ogly for image manipulation, text attack for attacking text, Armory for looking at other different types of defenses, and so on. But what are the consequences when one of these attacks take place? Well, attacking ML systems can be profitable for all kinds of adversaries, and ML is on course to be integrated into almost every industry. I think there was a study, I can't remember, is it even CompTIA, that said 86% of CEOs surveyed said that they use ML as a valuable part of their industry or within their company. So there's little to no security measures or regulation around ML at the moment, although regulation is coming in. But with any new technology, these things often run ahead of us before we can catch up and implement security in its place. So ML is kind of a little bit of a Wild West at the minute, kind of in almost a little bit of a parallel to kind of how antivirus was maybe about 20 odd years ago. The consequences of such an attack will be quite different for different types of targets, obviously. But you might have something as kind of benign as a denial of service, but when it's a denial of service that has the capacity to injure a human being, the severity can be much higher. So to categorize these types of attacks, we have to consider the goals of the attacker and the point within the ML lifecycle or the ML development lifecycle at which they strike. So as we mentioned before, by attacking an ML system, the adversary will usually aim to do one of three things. They'll attempt to alter the model's behavior. So this could be to make it biased, to make it inaccurate, or even malicious in nature. It could be to bypass and evade the model. And this would be, for example, to trigger an incorrect classification or avoid detection. So, if you think of like an antivirus model detecting malware, it would be coming up with a way of changing the malware so it's not, detected as malware. So it's classed as benign, or it will be to replicate the model itself. So as Marta talked about earlier, we can actually steal the model entirely just by querying it. If you can figure out enough of the training data coupled with this, you can create some pretty high accuracy knockoffs. And even with this, you're able to do these things we call oracle attacks, which I'll explain a little bit later. So in terms of timing, the attackers can target the learning algorithm in during the model training phase. And this is usually by poisoning the data or altering the training algorithms directly. So this requires access to the training data or access to the training process itself. And we'll touch on this in a short while, but this is quite important when you think of, you know, a static train it once model compared with a model that's learning continuously over time. And data poisoning can be basically incorporated into a model that's live. Alternatively, the attackers are, you know, if they're not able to basically get get to the you know, into the training phase, which they may not be, they may be able to hijack the model when it's in transit. You know, they could do things such as embed a backdoor, kind of in a different context to what you're probably used to. What we kind of refer to this as a neural backdoor, which acts almost like a skeleton key for the model. This is where you would have a particular piece of information that will force the model into triggering a certain type of behavior. So, you know, again, we'll rely on a mortgage approval model here for the same instance. You know, if it had a particular postcode in, then it would say, okay, always approve to this postcode. And, you know, the adversary could sell that to a third party. You know, they could sell access to this, you know, and this is how these things can be brought in. Now, also, we can embed traditional malware inside the model and deploy it that way. So we'll actually look at that towards the end of this presentation. And so if attackers actually have no access to the training process or to the deployment, but only an ability to query the model, you know, via a REST API, which is super common, if not probably the biggest use case for a model, be it, you know, internal or external. They can still attack the model by performing what we call as an inference attack. So inference is essentially used, or inference attacks, I think, will we go into inference in a second? Yes. Oh, yeah. We'll talk about inference in a second. But inference is basically where we can use evade correct classification. We can understand what's going on inside the model to create things to, you know, bypass it and so on. Or we can extract the whole model and steal it, which is which we'll again talk about. So yeah, sorry. Back to you.
Thank you. So let's look more in depth on at the poisoning attacks. Poisoning attacks are basically the attacks where the attacker can poison the data set that the model is trained on in order to make the model inaccurate, biased, or giving malicious outputs, for example. So in this scenario pictured here, we have a vision recognition model, visual recognition model, which takes a picture and says what's on that picture. And if the data set is poisoned enough, it can, for example, misclassify a picture of a cat as a turtle. That's a really benign scenario, really. But with a little bit of imagination, we can, for example, think of security scanners that could misclassify a gun as something benign, or other way around, and that might have profound consequences. In order to poison the model, the attackers have to have specific access to at least to the training data. And in some options, like in static or traditional machine learning scenario, in which the model is trained just once and deployed once, this is not as much of a risk. Now, most of the models that are surrounding us in everyday applications are trained on live data, on the data that user inputs, that user provides. So we call this online learning or continuous learning or adaptive learning. And in this case, the model is more adaptable to changes in user behavior, for example. It's more flexible, and it's a really great thing to keep the model's predictions accurate. But it's also a double-edged sword, because the users don't have to provide an honest data. They can modify their behaviors in a certain way, manipulate the data, and send manipulated data to the model. And if there is enough of those users, the models can be skewed. So those can be users, or those can be even bots, cyber criminals could come up with huge networks of bots that are sending manipulated data to the model in order to change its behavior. A variant of online learning is federated learning. I think it's good to mention it just briefly because it's used in many applications that are, for example, running on our phones, applications that are dealing with highly sensitive private data. So federated learning was something that is something that is supposed to address the problem of privacy, although it's not perfect, but at some level, it does addresses it by training the model on the user's device. So the data that we input into the model doesn't go anywhere. It stays on our device, and the model is trained on our device and then sent to the cloud to be merged with the global model. And in this way, for example, face recognition in Apple Photos works. So that's why Apple says, like, we are not sharing this data. This data stays on your phone. It's a great thing, obviously, because it attempts to preserve the privacy, even if it's not perfect. Well, nothing is perfect, but it also opens up for to attacks by malicious actors who can, for example, manipulate the model, the trained model, on the device, which is then sent to be merged with the global model. And at the moment, probably there is not much of validation made on the data set that is coming from the user or on the models that are going up to the cloud to be merged. So in this way, attackers can also try to manipulate the model. Most stark example of a crude attempt at data poisoning is the Microsoft chatbot Tai, which was released in 2016 and lived how many hours, or maybe a couple of days, I don't remember exactly right now, but it was shut down pretty quickly because users started sending, users just were being users, basically. They were not even malicious. They were just interacting with the bot in a way which made the bot racist, biased, malicious, and obnoxious. And Microsoft had to take the bot down immediately and rethink their way of training the chatbots. Now, with the next generation of chatbots, which is GPT-4 chatbots, this is becoming also a problem. And we can already think of nation states or big sophisticated adversaries training their own bots to be biased already, or trying to influence the bots that are there to actually push their agenda, be it political or any kind of agenda. So this might become a real problem. Now I'll give it back to Eoin to talk about inference attacks.
I knew we were talking about inference attacks. Cool. So we'll start first with the definition of inference. And inference is basically the process of, as we say, running live data against the model. So think of this as, a typical request or query to the model. You're inferring something, or it's responding to what the data you put in. Otherwise, in an adversarial ML context, we use inference to understand what's going on inside the model. So inferring what is happening inside there, be it decision boundaries, be it the way it weights particular features that it passes in. And we kind of use this as a data mining technique as the core of a lot of other attacks that follow after. So for most ML-based services, the user has to query the model with the live data, and by doing this, we can do three things with this. We can infer the decision boundaries, which is essentially determining what features will influence the classifier and get it to produce a particular outcome. We can reconstruct training data by doing things like membership set inference or membership inference. So understanding if based on the output classification of the the from the model of a particular input, we can determine if it was within the training data set. And through this, we can start to build up an idea of how the model was made, and then look to do something like recreating the model. So recreating the model can be done in a couple of ways. We can, recreate it from its training data set if we know enough about that. Or we can do something we call proxy modeling, or surrogate modeling, or also known as distillation, where we essentially we send a load of queries to the model over time, and from those inputs and outputs, we end up creating. We can train up a model on that itself, and create another model which can have a pretty high degree of accuracy, maybe not surpassing it, but even sometimes defensive distillation can be used, and it can make a model a bit more robust. But the thought of like having your model exposed on the endpoint, and somebody can just come along and steal it, is quite worrying, especially when you consider how much it costs in GPU these days, GPU resources, how much it costs in gathering the training data in the first place, how much it costs to crunch the numbers and the data scientists to build it. So what's really interesting then is that researchers at the Max Planck Institute released a paper called Knockoff Nets. And in doing this, they were able to create a surrogate model, or a proxy model, or a distilled model. Sorry, I shouldn't have said all three of the names. I should have just picked one. But they were able to, for as little as $30, create a reasonable knockoff of their models, of the target models. So again, we think back to what Marta's saying about the different adversaries and their different motivations. A foul-playing competitor could maybe look to steal a model that is exposed and then retrain or train their own and then deploy it. Or cyber criminals may want to try and recreate it to create an oracle attack, which is essentially using your distilled model as an oracle to understand if your attack will work. So you attack your own model that you've just trained up offline, and then you use that attack against the model that you initially targeted, and you can create attacks that have a really high degree, or a much higher degree of success, without ever alerting the main person that the attack has happened. So, and if we take this a bit further, stolen models could then be traded on underground forums, so this in the same manner as other intellectual property, or used to create unfiltered versions of chatbots. And, researchers at Stanford, so I suppose just up the road from here, which I only found out yesterday, were able to recreate the OpenAI, I think, one second, where is it now? Yeah, the OpenAI Text Da Vinci model, by fine-tuning Facebook or Meta's Llama model, and for I think as little as, they say cheaply. I think I've read something where it's about 500 quid or something like that. But anyway, so they were able to do that and recreate OpenAI's code generation model pretty quickly. And when you're able to do that so cheap with open source stuff, OpenAI's ChatGPT is obviously closed source largely, and that kind of thing. But if you're able to recreate it with the weights of Llama and just the outputs of the ChatGPT model, it's easy to see where these things can go. So. So I have a quote here from AI researcher Eliza Yukovsky saying, "If you allow sufficient access to your AI model, you're effectively giving your crown jewels to competitors that can clone your model without all the hard work you did to build and fine-tune your data set." So besides stealing the model itself, inference attacks can also help in model evasion attacks. And so these are essentially when we bypass or mislead the model. And, we go back and think of our malware analogy, because we used to be malware reverse engineers. So we always think of it through that lens. But, this is the act of modifying a piece of malware so that it can appear as, authoritatively benign to the classifier. It's also, we can bypass content filters, we can bypass spam detection, we can bypass EDR, MDR, IDS, IPS, fraud detection, and I suppose you can read the other two bullet points. But so it's pretty. We can bypass models. So maliciously crafted inputs to models are referred to as adversarial examples, and the purpose of an adversarial example is to evade the correct classification. So this is a picture of a cat here, and we just apply a little bit of noise to the cat, and all of a sudden it's being classified as a turtle with a 99% degree of accuracy. And it sounds a bit bizarre and probably looks a bit bizarre, but the image is almost imperceptible to the changes are almost imperceptible to the human eye, but to the input classifier it changes wildly. So in order to create these adversarial examples, the attacker basically perturbs the input in such a way that, when the model classification of the input, that the model classification changes. So, we like there's, even if we boil it down to like a super basic attack called a 1 pixel attack, we can basically take an image such as our cat here. We can iteratively modify a single pixel and trial it using differential evolution and modify it with a particular color, and we can ultimately end up with an adversarial example that does this drastic change in confidence with a single pixel. And we don't have a demo of that in this deck, but it's pretty mad to see. Pardon? Oh, sorry, saw somebody. Yeah. So yeah, I mean, like we think of it in the single pixel sense there, and it sounds a bit benign, but if we scale it out to something that's being used every day, we can see an adversarial example here where these adversarial stickers were put on stop signs, and what this ended up with is a self-driving car not recognizing that this is a stop sign. Now, you or I can see pretty much that's a graffitied stop sign and a stop sign with a few patches on it, but to an image or an image classification model, this can completely change their interpretation. So the possibilities are endless, and they can have many consequences. Now, we're going to try and just show a quick demo of a tool called Counterfeit here. Counterfeit is kind of an abstraction layer, an ease of use abstraction layer that's kind of Metasploit-like, you'll see in a second, that allows us to 1 second. Basically conduct adversarial attacks very easy and very quickly. In fact, so quickly that I might not have enough time to speak over this demo as we go. So what we have here is Counterfeit up and running. We're going to attack a credit fraud model that exists basically as a prepackaged model with the Counterfeit demo. We can list the target. Well, I might put that on a little higher setting because I think that's quite. Okay, we'll try this. So we can list the targets here. So we can see that we have our credit fraud model here. It's taking in tabular input. Next, we set our target to be the credit fraud model. Yeah, sorry. Not used to these cinema screens. So then we can list the attacks. So you can see there's tons of attacks bundled here with different frameworks. So adversarial robustness toolbox, Ogly, and text attack. We have the different categories, so evasion, inference, etc. And they use open box, closed box terminology here as well as the input data type. So for this attack, we're going to select an attack called hop, skip, jump, which is basically a query efficient way of determining decision boundaries of a target model and creating an adversarial example. So we say use hop, skip, jump, and then we hit run, and hey presto. So yeah, with this attack, we see this series of floating point numbers here. Now this doesn't really mean much to us, but it means something to the model. But what this is basically is a way of conducting fraud against a credit card classification model. And yes, the model itself, which is available up on Kaggle, has these numbers in as well, but they don't mean much to us because they've been de-anonymized, but they've been used by, I think they were given out by MasterCard and everything. So this is like from a pretty reliable data set. Cool. Right, get out of that. And that is not what I wanted. Can we move this? Where is it? Cool, lovely stuff. Thank God for that. We need to get the slides up again here. Yeah. Cool. So I'll let Marta talk about model hijacking attacks if we can get the notes up. Crap. We wing it?
I'll have to just look at the slide.
Yeah, okay.
All right, so we showed how the model can be attacked by the means only of having the access to the input and the output of the model. So if the attacker is able to basically query the model, they can perform inference attacks. They can, if the model is trained online on the user supplied data, the attackers can perform data poisoning attacks. The hijacking attacks require access to the model itself, to the model file. And even if this might sound like something that could be accessible only to like malicious third-party contractor or an insider, or requiring traditional security breach, nowadays many models are actually shipped together with the application. For example, our smartphone applications are often stored with the models themselves. So on the app stores, we can download the application, we can extract the model, perhaps hijack the model and re-upload it to the app store. Another thing is model zoos or model repositories. They are extremely popular right now. There are many of them, and they have vast amount of different kind of pre-trained models. And many companies are actually using those pre-trained models without much of a verification in their solutions. So they put those models in production, which can be really, really risky, because those repositories, they don't really have much of security checks. I mean, right now they are implementing them, and it's really good, and it's really great to see that the industry is moving fast to catch up with possible attack vectors. But still, they are limited, and there is no model integrity verification. If we think of an executable file, most of the executables nowadays are signed, so they have a digital signature that says that they are what they are, and they come from a trusted source, and were not tampered with. We don't have such a thing for the models yet. That's really important thing to ponder on. So the attackers might have access to the models, might actually those hijacking attacks might be a bit different than the inference attacks or poisoning attacks from that perspective, but there is a certain security risk here as well. So the first type of hijacking attack is actually an attack against the algorithm of the model itself. And this attack was demonstrated in academic circles. We didn't see anything right now in the wild that would use it. It requires quite a bit of technical knowledge, and it might be also very difficult to detect. So in neural networks, a backdoor can be injected into the model, even into already trained model. So the attacker doesn't require to have access to the training process. It can modify the model already trained and add something that we call neural payload, which is basically a rogue layer of neurons that will tell the model to do something that the attacker wants the model to do. So how such a backdoor works, it has two basic components. One is the trigger, which detects something that the attacker embedded in the image that will tell the model that to behave in a certain way. And if the trigger is detected, there is a conditional module with this behavior that the attacker would like the model to show. This could, for example, be used, as Eoin mentioned before, in loan approval applications. So if the attacker fills in an application with a certain little information in it that will not be really recognizable to a human eye, but the model will understand that this is the trigger, the model can say like, yes, this application is approved, even if it doesn't fulfill all the requirements. And there are many other possible scenarios. For example, in military, in ballistic defense or in detection of rockets and ballistic missiles, or in authorization. So the attacker could actually gain access to the resources that they shouldn't have access. So that's something that is really scary. We didn't see it happening in the wild yet, but it's also super difficult to detect. So it doesn't mean that those attacks are not happening. But there are also simpler ways for the cyber criminals, the usual cyber criminal, less sophisticated one, to actually abuse machine learning models. And machine learning models, before being put into production, they have to be serialized. So put in a format that is understandable, that is possible to store them in. And there are many serialization formats. Each machine learning library has its own format or uses a couple of different formats. And unfortunately, those were not really designed with security in mind, and many of them allow for arbitrary code execution. So that's another way in which the attacker can actually abuse machine learning model without attacking the technology itself, just using this technology as a way forward to gain, for example, access to the system or perform a more traditional attack. And a lot of noise was made around the Pickle serialization format, which is a Python module. This is something that researchers a couple of years ago demonstrated that it's possible to run arbitrary malicious code from a Pickle file. We tested it ourselves, and yes, it's possible. It's easy. We will show you a demo later. And Python documentation clearly states that this is not something that should be used in production, that this is not something that we should be trusting. But still, lots of models in Model Zeus are Pickle-based. And we don't know who uploaded those models there and what they can actually store. Another thing that can be done, which is also a bit of fun, is model steganography. Steganography, the traditional version of steganography, is hiding messages inside a picture, for example, which can't be seen. The picture looks like it was not modified, but there is something inside it. Also, malicious payloads can be stored in images like that, but they also can be stored in machine learning models. So this might be a bit technical slide, but this is inside of a ResNet model. We see the data PKL file, which is a Pickle, actually, a Pickle serialized model structure file. And then we have a bunch of files in the data folder which contain all the floating point numbers associated with the neural network. So if we open one of those files, what we see is basically floating point numbers. And in this way, in the same way as with traditional steganography, an attacker could modify those floating point values in order to store a payload inside them. So the attacker can modify as little as 3 bits, 3 least significant bits of all of those floating point numbers to store a payload inside the model without making the model less accurate. The model will be can be totally the same in accuracy, maybe with super slight change, but totally invisible to the human eye. In this example, we try to change 16 bytes, least significant bytes of a float. It gives a slight difference, not much of a difference, and in case of some models, that might be enough. But yeah, it's possible to do it with just 3 bits, and machine learning models nowadays are quite big, so even if it's just 3 bits of each of the float values, we should be able to inject quite a big payloads inside those models. Here we have a demo. Will be a bit funny. How do I do that?
Right, I'm now an expert. I'm now an expert on cinema screens.
Oh, let's put it in.
Yeah. Yeah. No, we'll go there.
Yeah, totally quality.
Cool. I'll start it.
And there's full screen.
Perfect. I'll just start it again as well. So
Yeah, pause it for a moment.
sorry, I thought I did. Good. Right. This is more difficult than it looks, I'll tell you that.
It would be easier if we had it there as well.
It's not letting me full screen it. This might have to do. Okay. Do you want to go?
So, is it visible? Oh.
Jeez. Man. There we go.
No.
Sweet.
If you just go to the beginning and stop it for a bit.
I'll just hold it.
All right. So, to showcase a scenario in which typical cyber criminal could use a machine learning model in order to gain foothold in a victim system, we developed a couple of scripts. It's nothing super sophisticated. So we have one script that will embed a payload, which we chose quantum ransomware for, just to showcase the scenario, but it could be anything really, any malware. And then another script to inject this payload inside the machine learning neural networks using the steganography technique that we showed before. And on top of that, we have one Python script that will decode this payload from the steganography embedded bits, reconstruct it, and run it. And finally, one script that will inject this previous script into memory. So it's just 4 scripts. It's nothing very complicated. And yeah, is it playing or?
Once again, yeah.
All right. Cool. So yeah, just to show that the scripts are not really complicated, a really quick run through them. Not gonna go into details, we don't have much time, but yeah, those are scripts. All of them are 50, 60 lines of code, maybe 100 with comments. So that's not really sophisticated. So let's see, we have a resonant model, original resonant model. We downloaded from the internet. We check the checksum, so to see that this model was not tampered with. That's the correct checksum that is shown off there. Now we embed our payload inside a shellcode. And we get the payload.py script, which is basically injecting this shellcode into the memory. And now we run our torch steganography script in order to inject that payload.py inside the model neurons. We found a layer big enough for it, embedded it. Now we can see that the hash of the file changed. It's not going to be any visual change in the model, just the hash changed. And now what we need to do is to inject our script, which will decode the payload inside the ResNet model using the serialization vulnerability. So now if we open the ResNet model, we can see that script in plain text there. It's crude. We could obviously obfuscate it, but for reason of this demo, it's totally enough. And last thing to do is see if that model will be loaded to the memory and what is going to happen. So we run Python import torch load, give the path to the model, and voila, the system is owned. Thank you. Yeah, that's the ransomware README note. All right.
Okay. go back up here. Oh, there we go.
All right, we need to breeze through the
Oh,
rest
no.
of the slides, really.
Right, we'll just go
Well,
with this.
We need to breeze.
Oh, yeah?
We don't have time.
Okay.
So yeah, just to summarize, the attacker could use those two techniques to actually perform, for example, supply chain attacks, or deploy malware or ransomware, or get a foothold inside a victim system. And this is not just proof of concept research. We actually are finding daily right now malicious files, malicious pickles, but not only pickles, also Keras models in VirusTotal or in those model repositories. So these things are happening already. They are crude attempts right now, but they are happening. So the rest is just closing notes.
Yeah. So I think we all know the stories of AI gone rogue, Skynet, the Cylons, to name a few. But we're not really there yet, and I think we really need to worry about us attacking AI rather than AI attacking us just at this minute, because it's in everything. It's ubiquitous. It's being introduced into every product you know about, and I can guarantee almost every product at RSA is going to be talking about their AI in their product. And so yeah, it's just okay. That's it.
All right. We don't have much time. These are some techniques to actually improve the security of machine learning models. So there are basically two approaches. One is to make the model more robust. It's a valid approach. Another one is to monitor the input and output to the model to see actually suspicious traffic. And I think we should combine both of those approaches together with definitely model signing, model integrity checks, and scanning for malware. We should just be aware that all those threats exist. Okay, that's it for today. We are out of time. Thank you. Thank you for coming.